this problem, okay, if I can state it as I stated it for you on the board, okay, we want to maximize the area given that. Now it was interesting. People tried to express the constraint that I had written about the bull hide, right? You had 20 meters of bull hide or 20 cubits or whatever I said, right? We tried to express that in different ways, and as I walked around, I'm going to show you several different things that people wrote. Some people wrote this, for instance. P equals 20. P standing for what? The perimeter. Now, then I got some interesting things. Some people actually wrote an equation for a perimeter, such as 2 times the length plus 2 times the width equals 20. Right? Some people wrote a different equation for a perimeter. 2 pi r equals 20. I'm going to put a little question mark there, because what's that the equation of? Circumference, which of course is, if you want, the perimeter of a circle. I mean, that was actually an interesting question I had was, are we allowed to use another shape? Am I constrained to a rectangle? And I'd have to read the legend or the God's verdict more carefully maybe for this. This is an interesting question, okay? Which I want to come back to, I think. I want to come back to that. By the way, one group not only wrote something like 2L plus 2W equals 20, but then they went farther, and they said that another way to write the constraint would be, say, L plus W is equal to what? 10. So that's interesting, I think. Right? So we want to somehow maximize the area given that you have some constraint. Of course, we also have formula for area. And I saw this sometimes. Some people wrote, we want to maximize area equals, say, if I'm using these variables, length times width, given that L plus W is 10. Are you with me out here? Okay. And I want to point out that there was a reason I picked the number 20. I'm not sure that that's exactly the right number in the Aeneid, but I am sure that's exactly the number that was in your book at the very beginning here. If you read the second paragraph, think about pairs of non-negative real numbers with the property that their sum is 20. X plus y is 20, right? Which has the greatest product, okay? And I said to myself when I read your book, I said, that's Dido's problem. I just don't know if 20 was the right number. Okay? I also don't know, but I'm glad you guys brought up, hey, am I allowed to think about other shapes? I'll get back to that before I leave this page, because it's a very interesting question that's been analyzed. But I want to go to how you tackle the problem if you say, no, you have to lay out the hide in a rectangle form. Okay? And so in your book, they actually made a nice little table, I think, of this. Okay? So let me show that. Here, yeah. So they try some values for x and y, and then they compute the product. Right? Notice that each one of them has x plus y. Oh, wait a minute. We do have a discrepancy, don't we? Mm-hmm. They're saying x plus y is equal to 20. So if I were to do the redo, my constraint would be maybe this, and then I would make it that. Is that okay? Fine. Same idea. Okay. So let's do that. Suppose that the perimeter has to be 40. Fine. Then I can just follow what the book did. It's the same idea. L plus W is 20. So here's a nice little table, and you'll notice that The best they came up with was 99, right? They did a 9 by 11 rectangle. Okay. But how do you know if you have the best? Can you beat it? Ten by 10 beats it, right? If I take 10 by 10, my product is 100. Can I beat that? How do you know? If you go 11 times a 9, you're on your way back down, right? That's what Jeff's saying here. I mean, it seems that 10 by 10, you're not going to beat it. If you move along here, we can take a look at this nice little, there's the discussion, but I want to move on to the applet they have here. I think this is really kind of cool. So they actually draw this graph in 3D. And the reason they do this is you say, well, look, we have X and Y, and then we're going to have a Z-axis coming off of the page. And so you can see we have the XY plane drawn. See that? And then what we can do is we can choose a value for X. So we could say, nah, I'm going to make X smaller. X is equal to 1.1, Y is equal to 18.9, and the product then is 20, right? And so if I want to maximize the product, you can see the reason they had to go 3 dimensions here is because there's really 2 inputs, right? The length and the width of my rectangle. You with me? So the length and width are the inputs, and the output is P, the product. You'll notice they call it the objective function. I'll talk about that in a minute, I think. But here we go. Moving right along, you guys suggested 10 by 10 would be the best product we can get. Let's see how that goes. Yep. The maximum product is 100. Once you get beyond that, you're moving back down. You with me? Now, what's the issue here? The issue here is I'd like to find that maximum for more challenging problems, and I'd like to show you kind of a whole technique we can use. Optimization, okay, is what it is. I'm going to go ahead and show you a few steps that the book lists in a minute, and then I'd like to actually solve this problem. So maybe we'll do that also. And then we're going to do some other examples. Here. Guidelines. Read the problem carefully, identify the variables, organize the given information, and then it says identify, step 2, the objective function. So on our picture here, you'll notice that I labeled this thing the constraint. But what you're trying to maximize here, it says we're trying to maximize this. This is going to become the objective function. Now the problem is, as I said, my objective function A right now is a function of 2 variables, right? A of L and W. And that's a problem. For now. Actually, 1 year from today, you'll be in Calc 3 somewhere. And in Calc 3, which is basically a repeat of Calc 1, but in 3D, you're going to do the same problem. You're going to say, oh, I can draw that graph, and I can do the calculus. Okay? But we're in Calc 1. Hold off, Paul. So in order to do the problem, what we need to do is we need to get this down to just a function of a single variable. That's where the constraint comes in. You see, what I can do is I can solve for one of the variables. How? What would I do? Subtract something from both sides, right? What do I subtract? L? Okay. So if I subtract L from both sides, now I have W is equal to 20 minus L. Right? And what I can do then is I can substitute where it used to say W, I can write 20 minus L. And as soon as I do that, what I'm trying to do now is I'm working with the objective function, which is Instead of W, we're writing 20 minus L here. So this is what I want to maximize. And I would say at this point, you have everything you need going into last exam if you want to find the maximum of that. Basically, what I want to do is take the derivative and set it equal to. How do you find maximum points of a function? What do you have to do? You have to find the critical values, right? So I'm going to want to compute a derivative here. If it were me, I would write a of L. Let's rewrite it. Let's write it as 20L minus L squared. Okay. Now I'm ready to take the derivative. What is a prime of L? (20) minus 2L. And so now I want to find the critical values. Okay. So we find critical values. And so I set the derivative equal to 0. And sure enough, 2L is 20, so L is 10. Which is exactly what we said should happen, right? You want to let the L, okay, equal 10. And then what I like is if you set it up this way, notice what you can do now. You can go back to the constraint. And if you substitute in here, you can also say W equals 20 minus 10, so W is 10, which means the ideal shape for our city is a square, if you're constrained to rectangles. Okay, if you're constrained to rectangles. By the way, what would be the maximum area? So the maximum area here would be 100. I guess the way I did the problem before, the maximum area would have been 25. I saw some people with that answer, 5, 5, 5, 5. Right, would add up to 20. So here's Dido's problem. Now, when I've taught Dido's problem before, I've always had people ask, well, are you allowed to use other shapes? Okay? And I think this is a very interesting question. And what, I guess all I can really do at this point is tell you that enough people asked this question in the 1600s that there were a few brothers that went by the last name of Bernoulli. You can look this up if you're interested. And they developed something called the calculus of variations. Okay? And I remember studying the subject actually in graduate school. Okay? So never in my undergraduate math degree did we study this, but in graduate school we did. And what it was basically going back to this section of Calc 1 again. But instead of having A of L, you would do something like this. You would maximize J of Y. J was called a functional, and the input is a function. And so what the Bernoullis basically were doing was studying different curves and trying to figure out, hey, of all these different functions we could describe, which one is the best at something? So for example, which one does give you the most area? Those of you that said circle, you are right. You may have been taught that in a science class, that a sphere somehow maximizes area for minimum surface area. These are facts we know now. And they come from calculus, but they come from a more advanced calculus called the calculus of variations. That's really where you have to go if you want that. But to learn that, hey, we have to learn this section. Then we'll move on to Calc 3, and then we'll move there in time. Okay? So just thought I'd throw that at you. I'm going to let you guys solve this in a second, but just so we can kind of see what's going on, right? Picture is over here on the side. You have a barn, right? Thank you. Wonderful barn. Thank you, thank you. And so you only have to, like the barn takes up some of the side, right? So you're okay that way. And so my fencing could look like this, or I could come out farther. I don't know. Right? Something like that. So maybe what we say is, picture-wise, okay, barn is going to make one side. And then I have, I don't know, I'll use X and Y, I guess. Why not? So again, we're trying to maximize or minimize here. We want to maximize area once again. Kind of like Dido's problem. This is an extended version of Dido's problem because the constraint is different, right? Area, if I use X and Y, is going to be X times Y. But what's my constraint going to be for this problem?
X plus, or 2 of your X plus your Y has to equal 200.
Right. If I do it that way, 2X plus Y has to equal, they say, 200 meters. Okay, so that's in meters. And so I think at this point, I'm kind of set, ready to go. Okay. What's the next step? We'd like to write area, not just like this, but we'd like to write area as a single function of just one variable. Does this make sense? So what do you do now? You solve for a variable over here. And I think in my mind, I would solve for the y. It's almost by itself. So I could say right away, y is equal to 200 minus 2x. And so the function you want to maximize would be x times 200 minus 2x, right? That's a function of x now. Now you can do calculus on it. Does this make sense? Okay. Let me turn you loose and try to finish the problem, and we'll go from there. If you finish the problem and want to try part B, that's not a bad idea either. All right, I'm going to finish up here. So we have a of x. Let me simplify that. Distribute the x. I think that makes it easier. By the way, I don't have to do that. I could just take the derivative and use the product rule, but this is easier, right? So we do this, and now we take the derivative. And so you guys got 200. Almost everybody got this now. Set it equal to 0, right? And so you get x is 50. And so then, so I want to make sure I answer the question. So let me look carefully at what it said. It said, what dimensions maximize the area of the pen? I got one of the dimensions, right? So the dimensions needed should be 50 meters by, well, we don't have the other part of this yet, right? So what do we do? Yeah, again, we substitute, right? You can take this x equals 50, go to the constraint. So you get y equals 200 minus 2 times 50, and so y equals 100, right? And so I think that's interesting. It's not a square this time, but it's a 2 by 1 rectangle if you want. Twice as long as it is wide would be the correct shape if you want when you put it up against a barn. This is a very classic problem. You guys follow? I think part B is really cool because it emphasizes that you have to be careful about what is the objective function. Here, let me pause just another second because not everyone got to read it. Read and talk to each other about what's the objective function and what's the constraint. The objective function this time, right? You want to minimize the length of the fence, right? That's different. So far the problems we've had have been maximizing area. Do you see how it's different? Matter of fact, what's the other thing that they tell me? Here, I'll draw it on my picture of my barn.
Yeah.
I mean, did they say four of these pens?
Yeah.
And each one was 100 meters squared, right? So they have this kind of picture in the book, right? And so I guess the constraint this time, you actually know the area, right? So if I call each of these segments, see if I keep the same way of doing this. There's multiple ways to do this. But if I keep this as x and that as y, here's an x, here's an x, and here's an x, right? But I guess my constraint is really that I know what the area is. How would you write that as an equation, the constraint? I would say, since we know the area, yeah, xy has to equal 400, right? Xy is equal to 400. And so what I'm minimizing here in part B is I want to minimize the length of the fence. And so I'm going to write L for the length of the fence. Now, how do you express L? Is it 5x? Let's see. 1, 2, 3, 4, 5x plus y. I like that. But, okay, go ahead.
What's L here?
That's really important. What is L?
Oh, it's just the length of the small one.
See how I wrote in words what I'm trying to maximize or minimize? I think it's essential that you do that. Always write, what's this thing called again? The objective, right? And so then what we want to come up with is we'd like to come up with what we're going to have the objective function. See, right now it's a function of two variables. I need like Calc 3 for that. You'll learn how to do this in Calc 3 again. But what we want to do now is we want to do it with just one variable. So can I do that? Well, I have to use the constraint, right? So talk to each other about what to do next. What do you do with the constraint so that we can make L a function of a single variable so we can do some calculus on it? Talk to each other about that for just a minute. So what can I write? I can write y equals what? Okay, 400 over x. And so now what I do is I substitute that y in here. And so now I have a single function of x, right? Which then I'll be able to take the derivative. You guys with me? So I'm going to write L of x is equal to 5x plus what? Yeah, 400 over x. Are you guys okay if I write it this way? I'm trying to save time. 400x to the negative first power. Is that okay? And why would I do that? That's the easy way to take the derivative, right? So we're going to take the derivative now. L prime of x, what does it equal? Oh, good question. What does it equal? Five. Question, Garrett? Never mind. Okay. So 5x becomes 5. What about 400x to the negative first? Bing! Minus 400. Bing! X to the negative second, right? You guys with me on that? Okay. So that's the derivative. And now I can try and find the critical values. And so to do the critical values, you're going to take the derivative and you figure out what makes it equal 0 and what makes it undefined, right? So let's see. 0 equals 5 minus, how can I write 400x to the negative 2? Yeah, 400 over x squared. Is that okay? This okay? And you should be able to solve this equation, I think. 400 over x squared is equal to 5. So 5x squared is equal to 400. So x squared is equal to 80. And so I get from this, I guess x is, well, it's interesting, because the rules of algebra say plus or minus the square root of 80, right? But we can't have negative in this problem because we're talking about a dimension of fence, right? So we're trying to minimize the length of the fence. I guess what I would do is I would use the square root of 80. Right? And now what does y equal? 400 over the square root of 80, which I get that y is actually equal to 5 square root of 80, I think, if I simplify that. 5 square root of 80. So I'm getting square root of 80, 5 square root of 80. And I know that can be simplified, but I'm just going to leave it as is. Guys get the idea? Any questions so far? I have a question. How do I know that that will be a minimum? I know it's a critical value, right? Or even up here. I said the dimensions for part A, the dimensions should be 50 by 100. And I said that'll maximize the area. How do I know it's really going to maximize the area? I guess I don't. All I know is it's a critical value. So I'm skipping a key step here. So I'm going to go back to part A for a second, and then maybe we'll talk about it in part B if we need to. How do I know that x equals 50? I know that's a critical value. How do I know that'll give me the maximum area? Go ahead, B. Say it a little louder. So that's one thing you can do. Pick a number on either side, right? And you could plug it into the function and just see, well, what are my areas that I get? Or you could plug it into the first derivative, right? On either side. That's that first derivative test we did. Or, how about the second derivative test? How does that work? Put the critical value. Actually, let me do that really quick, because this is actually the easiest way in this problem. What would be a double prime of x for this problem? Just -4. That's concave what? Down. Frown. Yeah, that tells me it was a maximum. You see that? So the second derivative is actually a really nice way to quickly see, yeah, we really did find a maximum. Here, let's try it for part B. Part B, I never found the second derivative, but I'm going to do that now. L double prime of x would be what? Well, 0, and then plus 800 x to the -3.
But it's positive though.
But it's positive.
So it's going to be
Concave up, cup. That shows that you really did find a minimum for part B. The reason I know it's positive is because I'm plugging in x as a positive number. I'm plugging in. So, yeah. So that second derivative test could come in handy also, so you could tell, do I really have a minimum? Do I really have a maximum? So I think that's good to see. So again, in number 20, which I'm looking at now, it says right away, number 20, we want to minimize what? Distance, right? They tell me that. And then the question is, what is my constraint? Well, find the point on the curve y equals x squared, closest to the point 18, 0. So what's the picture? I mean, the constraint is really going to be y equals x squared. They told me, here's the picture, right? We're trying to get as close as we can to the point 18, 0. Now, where would that be? I don't know. Here. Here's the point 18, 0. We know that the parabola goes through 0, 0. By the way, does anyone know what 18 squared is? That's not the answer, by the way. Right? What is it? 324? So way up here you have 18, 324. We know it goes through things like 1, 1 and 2, 4. This is not to scale. Right? It's a parabola. It's our good old parabola. Somewhere on that parabola, maybe we can beat 18. It's not going to be here. This distance would be 324. How do you find the distance, by the way? How do you find the distance from one point to another? Like, what if I thought the answer is 2 comma 4? Could it be? What?
Distance formula?
So we can use the distance formula. Yeah, what is the distance formula?
Equals the square root
Yeah?
x1.
Don't know it? Then we can use it.
Minus x2.
Minus x2 squared, right?
Plus y1 minus y2 squared.
There you go, okay? I'm going to say x instead of x2. And I'm going to say y1 minus y instead of y2. And the reason I'm going to do that is because I actually know what x1 and y1 are going to be. See if this makes sense to you guys. We're going to do this. We're going to say distance is equal to the square root of, if this is okay, I can do 18 minus x squared plus 0 minus y squared. Does that make sense to you guys? Because point number 1 is 18 comma 0. That point's never going to change, right? Point number 2 is going to change, so I'm going to call it x and y. Is this okay? And I'd like to simplify a little bit more. I'll just call it d. D is equal to the square root of. Are you guys okay if I write x minus 18 quantity squared? No?
Yes.
Yes? No? Are those the same? X minus 18 and 18 minus x? Not the same. But I'm squaring them. So if I do 18 minus 15, that's 3. But if I do 15 minus 18, that's negative 3. They're not the same, but if I square them, are they the same?
Yes.
Then they are. That's kind of like a nice little trick. If you don't like that, you could say, hey, put the point in for x2 instead of x1, right? I mean, this is another way to do this. Plus, and then here I have y squared, right? Now, I'm still not ready to do calculus on this. Why not? Well, because I have how many variables? 2. What I'd really like to have is that d is just a function of x. Right? That's what I'd like to have. So what am I going to do? That's right. We know that y is x squared, and so we can write y squared would be what, by the way? X to the 4th, right? Because it's x squared squared, right? And over here I have x minus 18 squared. And I wrote parentheses because I'm not going to write square root anymore. I'm going to write the whole thing to what power? 1/2. Okay. Next, d prime of x equals. Oh. Can you guys find the derivative of this thing? Bing. Bing. Bong. Yuck. Nice fact to save time and headache. If d of x is the square root of f of x, then d of x will be maximized when f of x is maximized. Yeah, Garrett?
When you're at the beginning and you're at d equals x minus b squared plus y squared minus squared root, are you able to cancel those, like the square root and the squared?
No. Why not?
Yeah.
What's the one thing that keeps me from canceling the squares and the square roots? That plus.
Okay.
If that were at times, you can.
Okay.
That's a good question. So no, I'm kind of stuck. But what I can do instead, and this is a cool fact that you can use specifically for distance problems. If that distance formula is involved, you guys, it has a square root. The square root is what makes this thing horrible. But I know what the graph of the square root looks like. The graph of the square root, it's a one-to-one function, right? It increases like that. And so it turns out that since the square root function is always increasing, whatever it is that'll maximize f of x, that'll also maximize the square root of f of x. If you believe that fact, we can make the problem a lot easier. So allow me to do this. Instead, let's maximize what? F of x is equal to, well, just the inside part, not the 1/2 power. F of x is, we said, x minus 18 squared plus x to the 4th. Let's maximize that. Is that okay with you guys? Here we go then. Let's maximize it. So what do? F prime of x is equal to 2 times x minus 18 to the 1st power times 1, right? Plus what? 4x cubed. So that's what I'm going to maximize. So here I go. F prime of x, I'll set it equal to 0. 0 is equal to, we get 4x cubed plus 2x minus 36 if I set that equal to 0. And I'll say this, that's still not an easy equation to solve, but do you agree with me it's going to be easier than the purple one? Okay, so let's go with it. So how do I solve a cubic equation? It's funny, this is exactly what my college algebra class is doing right now. And they're doing things like, find the factors of 36. Here, let's divide both sides by 2. So now I have, let's see, 0 is equal to 2x cubed plus x minus 18. Maybe a calculator can help me here. Let's try this. Let's try, I'll pull out the calculator. I'll type in y equals 2x cubed plus x minus 18 and go from there. So let's see. Y equals 2x cubed plus x minus 18. Graph. There it is. Hey, what's it look like it goes through? You think 2 is the answer? I can check that, right? So the college algebra way of doing it, what we're doing right now, if we think 2 is the answer, then we're putting the coefficients right across the top and doing synthetic division. Do you guys remember this? from years ago, maybe. I add and multiply. How many have never seen what I'm doing here? How many have seen this? Okay. 2 times 4 is 8. 8 plus 1 is 9. 2 times 9 is 8. Hey, it works! What I just showed, because this is a zero remainder, what I just showed is that this equation can be factored into x minus 2 times 2x squared plus 4x plus 9. If you don't believe me, you can multiply it out and check my work. Or another way to do it is this. Look, once I think 2 is an answer, right, just try it. What's 2 cubed? 8 times 2 plus 2. 18. Minus 18 is 0. It really works. So one of the critical values is x equals 2. Oh, but does that critical value give me a maximum? I do too. Let's check. All right. What is f prime of x? It's 2x cubed plus x minus 18. What is f double prime of x? It is 6x squared plus 1. Hey, 6x squared plus 1 is always positive because x squared, right, can't be negative. And then we add 1 to that, which means we are concave up, cup. And so x equals 2 gives me this will minimize f of x. Therefore, also minimizes d of x. Wow. That was a lot of work. But we did it. We figured out that if you want to minimize the distance, you need to use x equals what? 2. That'll minimize the distance. And so looking here, all right, I can see that that orange line I drew from 2,4 to 18,0 is actually the minimum distance you can have between a parabola and 18,0. They must have picked 18,0 because it works out really nicely to a point that everyone knows. I think that's really cool. Hey, what would be the minimum distance? Can we figure that out? Well, sure. How would we figure it out? We could take this function here, this d of x function, and plug in 2. Let's do that. D of 2 would be the square root of, if I plug a 2 in here, minus 18, so I'm getting negative 16 squared plus, and then 2 to the 4th power is 16, right? So I'm getting the square root of, well, it's funny because it's 16 squared plus 16, right? And this is actually what Garrett's question was earlier. Can I just take the square root of each one of these? No. But what I'm going to do is I'm going to factor out a 16 times 1 squared plus 1. 1 plus 1 is 2. So I get 4 radical 2 is the distance. That's the minimum distance you can get. Or another way to say it is, it's the square root of, let's see, 256 and 16 would be 272. How big is 272? Square root? Well, it's less than 18, right? So square root of 272. Yeah, 16, and you can get below 16 and a half. And then it starts increasing again until by the time you're above it, it's 324 above. That's kind of nice. You guys, on your paper, and I'm getting a blank sheet, I'm going to write down, I'm trying to minimize the length of the crease. And then what's the constraint The constraint is that the point P has to be on the opposite side. All right, so this is a little bit interesting, I think. I'm going to draw the same picture they have as best I can. A, B, here's point P. And then we put point P somewhere on the opposite side. And so the picture they're showing is something like this. And so I guess point P ends up over here, right, after this little corner is drawn. Oh, but one difference between my picture and their picture is that this is your crease, not that, right? You make one fold. So that orange line, that's the L I'm interested in. I want to minimize L. Now what I really want to do here is ask, can we figure out how to define L? Well, there's another interesting fact, which is this is a right angle, right? So if that's a right angle, that's a right angle. And so I can use the Pythagorean theorem. I can say L squared is equal to I don't know what squared plus I don't know what squared, right? Let's call those things something. Let's call this thing x and y. So x squared plus y squared. L squared is x squared plus y squared. And so what I would really like to do here is I want to minimize L is the square root of x squared plus y squared. Of course, my issue here is I'm supposed to do this in terms of a and b. And I just made up two new variables. That doesn't really help. Of course, I do see some things going on here. Like this length right here. Do you guys know how long that is? A minus x, I agree. And then, similarly, I can label this side length up here would be b minus y. Right? And what would be really nice is if I could say something about this length right here next. Because if I could say something about this, I could relate it to A. So I'm not sure about this yet.
That's a right triangle.
What's that?
You know that little triangle, there's a right triangle.
Yes.
The-
This is a right triangle here. That's the key.
X and AX, or A minus X.
And as a matter of fact, do you see how x is the hypotenuse of a right triangle? You guys see that? I just don't know the length of this purple segment yet. But what I also see is that if I draw a perpendicular line here, I'm getting both a rectangle and a right triangle again, where y is the hypotenuse. So I see a lot of stuff going on here. Okay? Triangle number 1, I'll call, and triangle number 2, I'll call that. This length here is b minus y, this rectangle. But I have a feeling I don't need that. Okay? This length here, I can call z. And if I do that, then I can call this length here y minus z. Because again, from here to here, we're calling y. Okay, so here I go. Remember that this is A. So triangle number 1. a squared plus y minus z squared is equal to y squared. Okay. Triangle number 2. And after I write this equation, I'm going to say I'm out of time. This will be z squared plus a minus x quantity squared is equal to x squared. What I think we can do, guys, is make some substitutions in here for x squared and y squared. Okay, I have to think a little more. That's kind of my first instinct on where to go. We could go with that tomorrow, Wednesday.